kin, right? Um, all right. So this is the first time I've ever streamed anything on this channel, and maybe you might know me from my blog, or realistically, the people watching this are in Handmade Hero or in the Handmade networks. They already know what this stream is primarily focused on, but just for quick explanation, right? Um, so we are making a virtual machine for the Handmade Hero learning jam, right? So learning jam that's going on, right? And this live stream is part of the second week. If I can find an explanation or whatever, this is part of the second week, and where I'm sharing what I've learned. And I spent the past week learning about this, which is an attempt to make a virtual computer for my own projects, and maybe for other people to use as well. So that's the plan, and so we're gonna get started on this. So first of all, what's the point of making a virtual machine? So I have okay, if we first go over here, right? So let's just drag this over here. We do that is too big. So we're first gonna ask why we're doing this, right? So essentially, most I dislike programming on most systems, right? Uh, Programming. So programming for most computer systems is kind of annoying, right? And it's like a lot more complicated than it needs to be. So programming for this is too big. So yeah, so programming for OS is equal to it's very annoying, right? So um there's all this there's all these differing APIs that you have to work with if you're trying to make a program that's actually matters, or a program that's like typically useful, right? And the problem is that none of these patterns are the same on each operating system, right? So every why is the text so big? Yeah, that's fine. Every OS is different, right? So Linux has its own APIs, Windows has its own APIs, Mac and Apple devices have their own APIs. So if you want to make a program that runs on all of these different platforms, s- again, like I said, it's pretty annoying, right? So so I basically want something that lets me abstract, that lets me extract over um abstract also, and that lets you abstract over the annoying parts of OS design and things that are more complicated, right? So what does OS stand for? It stands for operating system. Okay. So um so if you look at APIs like the Windows API, so MSDN, that's not a thing anymore apparently. Microsoft.com. So if you look at Microsoft's APIs, this isn't actually their WinMain, Learn, Windows, Open, Window. or like so if you look at something like this, right? You have to register a class name, you have to do this, you have to do that, right? And all of it's like this part is kind of as simple as it gets when like creating multimedia applications. So it's a bit like it's more complicated it's more complicated than I think it should be, and especially once you go to things like Linux and XCB and Wayland and stuff like that. It's really annoying to manage like all these different systems and make a cross-platform application. So by having a virtual machine, which is what VM stands for, everyone knows that. Virtual machine. So by having a virtual machine, you can just um you can just isolate all of that, and then you have one version of your program that runs everywhere, kind of like what Java promised. But the way I want to do mine is a bit different. Another reason why I'm doing this is because this year, no, why is it? Another reason why I'm doing this is I need to stop like middle clicking it. Okay, yeah. Is for the learning jam, which I already talked about, but last year last year Handmade Network did the visibility jams and the real wheel invention and the wheel reinvention jams. And I, for some reason, decided not to take part in those, even though those would have been great practice. But you know, um, this year, hopefully, we'll take part in all of the jams, and we'll know what you will have some interesting projects out by the end of it. And thirdly, looking into this stuff has been very interesting, which cool thing when you're working is if your work isn't enjoyable to do, then you should stop doing it. Or if the work isn't at least interesting to you, then you're not gonna have too much fun. And that's what we're all about here, right? So now we're gonna move on to what virtual machine is, right? So virtual machine is just a piece of software that pretends it's another computer, right? And the way it does this is, as we'll see later on when I actually program a basic version of one of these, is that they pass instructions. They get instructions from from memory. Sorry, they pass instructions, and then they decode these instructions live, right? And there are two approaches for how you can design your VM for how it can be run, right? There's three technically. So there's emulators, which are virtual machines, which are things like which things are like Citra, DS emulators, Apple II emulators, stuff like this, that takes the design of a real computer and mimics it to try and run programs designed for that computer on hardware that it wasn't intended for. And then you have fantasy computers, which completely just don't, which are like completely custom designed computers. The most famous one of these is Pico 8. So we can look for that. Most people know about these. So Pico 8 is a fantasy console that lets you like program games in your own little like sort of system, right? And the way this works is it as far as I know, I think this is closer to just like a normal game engine than like a real like fantasy console. But it is like it for what I'm talking about, it's basically a fantasy console. It gives you gives you a set like some restrictions like screen size, part size, um how many instructions run per second, stuff like this. In order to like give you a more limiting experience, which makes programming more interesting, right? So, um, fancy computers, they never existed before, and we're making one in order to abstract over computer hardware, right? So let's go more into how you can actually do these fancy VMs, right? So there's two different ways that you can approach doing these. First one is a stack VM, and the second, which we'll actually be making today, is a register VM, right? So a stack virtual machine is a lot simpler than the register VM, but the register VM is typically faster and nicer to program assembly for, which is kind of important for what we're doing. So stack VM is sort of like, it's like you take the construct of a stack on in like your programming language, and the stack is normally just like uh area of memory where you can add data to the top of it, remove it from the top of it, things like that, and you can do operations on it. And then um and these are the only ways you can store data, right? So stack VMs, um a good example of a stack VM actually is UXN, right? UXN is one of the main inspirations for actually doing this whole thing, and it's a really cool virtual stack machine. And it's really simple. You just have stacks of bytes that you use instructions like these to increment to put data onto the stack, sorry. And then you can run commands like jump, swap, pop, in order to like manipulate data on this stack, right? So that's like it's really simple, but provides like enough control over data to produce actually useful programs. So um so that's a stack VM. Now register VM is much closer to an actual computer, right? So computers, you have your CPU, which accesses memory, and then there's registers inside the CPU. So if you look in the CPU, there's like little areas. Normally, you like visualize them as boxes, right? Little areas of in your CPU, like one, two, three. You can store data in these boxes, and each data in the box it can be of a certain size. And since it's literally on the CPU itself, it's really like really fast, right? So that's what you call registers, right? So this is a register, and register VMs are a lot faster than well, not necessarily a lot faster, but they can be more optimized, in my opinion, at least so far from what I've seen over these few days. From what I've seen, you can optimize a register VM better than you can optimize a stack VM. Although that is typically, thanks to Negate for telling me this, but that's because you're able to. That's because for stack VMs, you normally use those for languages, right? So, and you're normally generating it. Normally generating it from like an abstract syntax tree, right? So, lang. Yeah, so you're normally generating the stack bytecode in a VM from an abstract syntax tree, right? Which means that you don't need to do as many stack operations, which are expensive. Register VM is more for like making your own like sort of CPU, right? So for what I want to do, register VM is better because I want to perform optimizate more optimizations, right? And also, if you've seen anything on my blog, you'll know that one of the primary reasons that I want to write this is I want to make this as an OS abstraction layer that you can optionally, obviously I may provide a scripting language that you can program over the top of it with, but the primary goal is to write it in like assembly or like in a compiled version of a language, right? So we're gonna be making a register VM. All right, so let's stop just randomly talking. Let's get into actually programming something, right? So done these. So now we're gonna go over the general VM structure while we actually program it, right? So I have this repo that I'm gonna upload after the live stream, which is a generic virtual machine. You can see all of this. I'll publish it later, but um, for now you're just gonna have to watch me program it, right? So we're gonna create a new folder in Geppetto called um. We'll set up the build later, but yeah, for now what I want to do. I don't want to get bogged down by like build script stuff or whatever. But for now, I'm gonna create a folder called source. I'm going to well, actually not gonna actually not that doesn't make too much sense. We're just gonna make a new file here called um Geppetto. Wait, we're gonna call it vm.odin. Is it jep vm.odin? This is actually gonna contain more than one package, so we're gonna contain more than one thing, so it actually might make sense to make a folder. So we're gonna make a folder called jepvm, save jepvm. We're gonna drag this. We're gonna move this, rename to actually no. How do you move it? Save folder. Yeah. So we're gonna move this into jepvm.odin, right? So let's go in here and let's start programming an actual VM, right? So the main structure of a virtual machine is as follows, right? So you let's just paste this in here, right? So you want to loop over, you want to load a file into memory. You want to loop over instructions in that memory, and you want to get the opcode and arguments needed to execute the instructions, and they execute the instructions, right? So we're gonna ignore this for now because that involves us actually having a file format, and we don't have that yet. So for now, first thing we're gonna do, we're just gonna find some memory up here to be memory. Um, what did I say for how much memory we're gonna have? We said yeah. So we're just gonna have a dynamic 64 of however much memory we need, and for now we're just gonna reserve for memory like I don't know 1000, right? So for now, we're gonna store 1024 actually, 1024 U64s for memory for now. So now let's get started. So we need some registers in order to be able to loop over these instructions. So for registers, what you're gonna need is the system that I've designed, right? We're gonna go into memory and we're gonna have a look at this, right? So we know we've already done this section. We've got a 64-bit address space, Odin's uses for yada yada yada, right? So, unlike actual computers, which have a limited set of registers, I devised a system that is technically an infinite amount of registers, right? Mostly because we don't have the physical limitation of actually having to limit the amount of registers we have, and instead it's more convenient to have a lot of registers, right? So, first we have global registers, which there are a limited number of, right? So we're gonna define these, right? So we got we're actually gonna define this in a new area. We'll do import reg dot slash registers. Gonna create a new folder, save that to be in folder new register registers global dot Odin. Yep. So we have our GI register, which is our instruction pointer, which is initialized to 0, right? So we're gonna have um is it useful. So all of the registers in the system are 64-bit. Now we have GI, which is a U64 instruction pointer. We are gonna have G. What else did I say here? Where's memory? We're gonna have GS, which is our global stack pointer. Gonna have GB, which is our base pointer. I'll explain that in a second. We'll have GR, GR, this is 4, and we'll have GL. Alright. So let's go over what each of these registers does. So instruction pointer, everybody knows what this is. It stores the address of the next instruction to be executed in memory, right? And that starts at 0, mostly because that's just easier to start at 0. Then we have our stack pointer, which points to the top of the stack, and so the top of the so we initialize it to 0, which means it has to be set before stack operations can be used for reasons you'll see in a second. The base pointer stores the address of the bottom of the stack, and similarly to the stack pointer, you also have to initialize this before using stack operations. And I'm gonna actually explain what any of that means, right? So, if we go over here. Now, I just got done talking about how I'm not making a stack based machine. So why am I talking about the stack again, right? Well, even in register machines like your actual computer, stacks are a very useful thing for example, when you're writing subroutines, you save you save the date, you can like save the address they jumped from, for example. Although in my system you might not need this for reasons you're gonna see. Um and storing parameters, for example, and just things like this, right? So because we have this, let's have a look at how that actually works, right? So you have GS and you have GB, right? So GB and GS, when you first initialize them, should be the same value, right? So when they're first initialized, they're 0, but they can't be 0 because um the way you actually increment the stack is downwards, right? So when you push a new value onto the stack, um a piece of when you push a new value onto the stack, the data that you've pushed onto the stack is put in at the position GS. So wherever GS is, so if it's at like address 5F or something, the data will be put at 5F. Then your stack pointer will be incremented by the size of the data that you push onto it. So most commonly, since it's a 64-bit machine and we're not really too concerned with memory, or not really too concerned with like using big integers or whatever, you're probably going to be incrementing it by fives, right? So you're going to add, you're going to actually remove 5, you're going to subtract 5, right? And the reason we do subtraction is mostly a historical thing, but also in case the VM implementation that you're using might have like a maximum memory limit, I think it would be very convenient to just put the stack at the top of put the stack at like the end of memory, and then that's however big your stack is, right? So you subtract from GS um like 8, right? Now that you've done this, right? If you want to do the other thing, if you want to do it the other way, and you want to pop data off the stack, you simply add, right? Now you might be wondering, that data still there. Well, that data itself doesn't actually matter, because next time we use it, it'll just get overwritten, right? So essentially, remove the data from the stack because nobody really cares about it anymore, right? So, um, now, so the reason we have a base pointer is, for example, if you want to clear the whole stack, you can just move you can move into GS, you can move into the stack pointer position of the base pointer, and that basically clears the whole stack, right? And then on top of that, if you want to like just ignore whatever's below, you can just set the base pointer to be the current member of the stack, right? So move G B G S. Alright. So we got subtracting, which is you push something to the top of the stack. Then you pop something by adding value, which essentially like ignores that value. So next time you push something, it overwrites it. And you have move GSGB, which is essentially clearing the stack by setting the GS register to be the base pointer and ignoring everything, and then just ignoring what's happened so far by moving GS into that, right? So before the stack can be used, you obviously have to set these two values, right? The return register, um, so in my system, unlike in other computers, right, normally the return value is stored in like the return value of subroutines, right? So subroutines are just smaller sections of code, right? And normally they have a return value. So um they're normally stored in Intel machines or like in x86 machines, stored in the EAX register, right? And my equivalent to that is just the GR register, right? So I'm going to, for now, stick to just having one return register because I can't think of too many instances where you need more than one return register, but we'll see how it goes, right? So now we get to the part of the system that's a bit more interesting, right? So unlike an actual computer, we aren't limited by physical space, right? So unlike an actual computer, we aren't limited by the fact that like you have to account for transistors and all this, right? So in my system, I've just decided we're gonna have infinite registers, right? And there's a lot of utility in this, mostly because it prevents us having to use a stack for things other than just saving, um, you know, other than just like saving, seldom data, right? So if you save like stack use in this computer won't be very common. You'd probably use it relatively infrequently, mostly because doing things on the stack, you're accessing memory, The main reason you have registers in actual computers because accessing memory in real computers is slow, right? It's slow compared to just accessing the CPU, mostly because the RAM is a lot farther away. But in our machine, we're gonna have the same speed regardless because all of our program is stored in memory. Although some of it might notice that some pieces of data are being used very frequently and use some of them in registers, but that's besides the point. So the speed isn't the main concern, but it's just mostly the utility of just being able to um have more than like say 8 registers, for example, in like x86, I think has 8, or it might be, I don't know. So um so obviously in some systems, like I think in the Lua virtual machine, which was a great inspiration for this, you can just like, or in a video I saw by like Ledo, great channel by the way. um he showed that you can just have like, he essentially explained register VMs to be normal like stack VMs, where you can just assign values to like different things, right? Which is kind of like a simplification of what it is, but it's pretty accurate to what I kind of want, right? So I was originally just gonna let you index any VM, any register that you wanted, but I was thinking that wouldn't make too much, like that would make register overuse a bit egregious, right? So I've decided to make some sort of like interesting. It would also make the actual bytecode, or it would make the bytecode and the indexing of registers like a lot more annoying, right? In both assembly and when it's actually compiled, right? So I've decided to employ register windows, right? So register windows are a real technique that were used in computers that I'll show you in a sec, which basically means that there's in real computers there's still a maximum amount of registers in the actual computer, but um they locked some of them away from you and didn't let you see some of them. So you had to you had to change something relating to the computer state before you could access the register windows, right? So if you go to, let me check this out. Go to register windows on Wikipedia. Systems like Berkeley's Risk Design, the Spark architecture by Sun Systems, and the Infineon C166. Yeah, so these are like so essentially, depending on the state of the program, you can access a set of like 8 registers, right? So this set of 8 registers um is a subset of like a total amount of like 64, for example, in the Berkeley design, and it makes the code more readable instead of having like something like add instead of having like add like hash, which is like to index a register like 20931 or whatever, right? Because you could theoretically in my system have this many registers. Instead, I've limited the ones you can access in a scope to 16, right? So you can access 16. So for any of this to make sense, I'm gonna have to just continue with the design, right? So in here, if we go into Japel VM, we have so in our registers we have GL, right? And GL stands for global local register, right? So this global local register um basically stores an index into an array that you are about to see right now. I'm actually gonna rename this file to just be registers installed in. Yep. So there is a series of registers that I'm just gonna call local, right? And this is another dynamic U64, another dynamic U64 of another dynamic array of 64-bit integers, right? For your registers. And this array obviously is infinite, as I've already explained. So you can only actually access 16 registers at a time. And the reason I've decided this is, as I already explained, it makes it easier to reason about the code. So, how do you tell which 16 registers in this local array are we actually going to use? Well, this global locals stores an index into an array into this array, which is the offset of how many registers you can access, right? So, in order for this to work, we're gonna need some way to limit the trying to figure out how you can explain this, but GL is essentially an offset to indexes into this array. And so whenever opcodes ask for register 1, 2, 3, 4, 5, 6, 7, 8, whatever, right? I actually have to change this quickly to be L1. There you go. Yeah, so whenever they ask for indexes into this thing, it bases it off of GL, right? So when your program first starts, since this is 0, it'll get the first 16 registers. And then if you change it to be like 50, it'll get 50. L0 will be equal to local 50 plus 1, right? Or 50 plus 2 or whatever, right? So that's how we're gonna do it. And in order to do this, I'm thinking whether we need a function for this or not. We might not need a function, but it might make it easier to have a function. But I cannot think if we're going to need a function. Hmm. We're gonna do local get. Yeah, so we're gonna have a procedure for this. So you're not actually gonna need to see this, so this can just be private. And we're gonna have a procedure that takes in U64 of index, and it returns you a local register U64, which returns index, which returns the value in the register um of registers no turns the value at index plus offset, right? And obviously for this we're also going to need a matching set statement, right? So the reason we're going to need a getter and setter for this is because it would probably be a bit bothersome to have to set it would be a bit bothersome to have to like manually add to the value each time that you need to get the local, right? So this is good for utility, right? So get we'll set u16, or like the value you can set, yeah, um value, they're both u64, so I can just do that. And then you reset the value at local index plus your offset plus not offset, sorry, GL plus at GL. That's actually what I meant to put here. Set that equal to whatever value you put here. So essentially, every time you want to index into local get, you are actually indexing into a register that's been offset by this GL, right? And some instructions or rather some macros, which I'll get into when I make the assembler, either tomorrow or probably next week or over the coming weeks. You can have some macros that add to this when you make a new scope, for example, and yeah. So we've basically sorted all of the registers and memory that we're going to need to concern ourselves with, right? So now let's actually get into some instructions. So the basic thing that we want to do is we want to have a variable that tells us if we're running, first of all. Running is true. And then we're gonna have an infinite loop that keeps looping while running is true, right? So these these instructions, so these two sections have to be are only run while it's running, right? So the way you get the next instruction is you go into memory and you get the value at the current index. They get the value at this using the index of gi. So gi is our instruction pointer, like we talked about before, and the way you can get that is memory is you can do opcode is equal to memory registers dot gi. Right, so we've gone our opcode and now we need to parse it. So most of the parsing is going to be pretty similar, right? So I'm thinking that we might need to. Actually, this doesn't need to be in just leave it like that. So we're gonna need a function that we're gonna need a type and a function that decodes our opcode into um into what we actually need from it, right? Because otherwise, actually, wait, we might not need that, but it might be useful to have that later. Because basically, as part of learning for this jam, I made an LC3 VM, which is a little computer 3. And currently, what I did in this machine is I had it like we were basically decoding the operation on the fly, which can work, but I feel like we'll see how it goes. We'll see how it goes. I feel like it could get a bit out of hand, but hopefully not. So what we're gonna do is we want to get we want to first get the whole instruction, right? So the whole instruction is at memory reference at memory registers gi. So that's the instruction that we want, right? Now we want to get the opcode, right? So normally most of you probably know this, but in computers opcodes are like, I'll just show you. Essentially in computers, um let's say find it. But essentially, instructions are represented as a bunch of bytes, right? Like everything else in a computer. So, what an opcode is essentially, vision this is your entire instruction, which is your entire byte. Your opcode tells you initially the type of the byte, right? So a certain number of bits in this number, in this binary number, tell you what type of instruction it is. And this is important to have because that then tells you how you decode the rest of this, what arguments go after here, and then all of that. So after your opcode, you have your arguments for what you need to do to perform the instruction. And those vary depending on the instruction itself, right? So opcode um so if you want to get our opcode from our instruction, I've now decided that if I go into instruction, I go here, just now decided that we will have a maximum of 256 instructions. Realistically, we're not going to need that, but Um, it's useful to have in case I ever decide to expand the VM later, right? So we have maximum of 256 instructions, which means that opcode is always 8 bits. So the first byte of every instruction is an opcode. Let's go here, define that. We'll go instruction move to the left by we just want mouse C3VM. Yeah, we just want the bits that we want is the first 8 bits. Alright, so if it's a 64-bit number, 64 minus 8, 56. And this gives us just the 8 bits of our instruction, right? And it's probably safer to store it as a U8. That way we know for a fact that it's 8 bits and we don't have to worry about anything else. So now we have the first 8 bits of our instruction, right? Um, and we're gonna do a switch on which 8 bits these are, right? So in case we don't know what these 8 bits are, meaning they're not in the instruction set, we are just going to, for now, I maybe later we'll have a proper, like debug log or whatever, but for the time being, we are going to simply just print empty.println invalid instruction by instruction skipping, right? And then that's the end of the loop. Oops, one more thing that I forgot to mention is that at the end of this loop, in order to make sure we actually go to another instruction, we have to do registers.gi plus equals 1. So every time we execute an instruction, we increment um the GI register so that when we get it next time, it's a new register, right? It's a new instruction. So we have our, yep, this is actually not correct. So you need to get the opcode for your instruction first, then you execute the instruction, and then you just increment your pointer, right? So the way you, so let's, for example, we'll do first instruction we're going to do is the move instruction, right? So I'm actually going to not find, I'll just have, I'm thinking. So in the LC3 VM, um, I actually had an opcode type which just has all the codes. Um, we already have this as a U8, but it might make more sense to do it as an opcode actually. So we're gonna define an opcode type. We're gonna define. We're gonna define an opcode type so that way that if we miss an opcode or something, then we know we've done it wrong, right? So that means that instead of converting this to a U8, we're actually just gonna convert this to an opcode type. That's how you get that, right? So now we're gonna do a switch on these opcodes. And in the first case, we're gonna handle is the move instruction, right? So the move instruction, all right. So what we're gonna do in this stream, we're gonna do hmm, we'll do a few instructions, right? So we'll do a few instructions from each of these categories, right? So we're gonna do if arithmetic instructions, data flow instructions, and control flow instructions. So the first instruction we're going to do is a control flow instruction. which is the move instruction, right? So, um, what do we want the opcode of this to be? I think I want instruction 0 be the address to be the move instruction. Although we might, since we've put it as an enum, it's relatively easy to change the opcode by just changing. It's relatively easy to change the opcode of the instruction by simply just changing the number, the order of the opcodes in the enum type. But you know, we're actually going to do this in a way. We'll see how the instruction set grows as we go. But essentially, we have these three classes of instructions, and the first one we're going to do is the move instruction, right? So the move instruction, let's see what we're gonna choose for how it's actually laid out, right? So move instruction, we're gonna say obviously the first 8 bytes are the actual opcode, which is 000 000 000, and then the next. So the move instruction can have many different variants. You can have move register to register. You can have move. Thing about move is that it's not really like a move. I'm actually gonna call it copy in my system, mostly just because just trying to be different. I guess I don't know. It's probably not too much reason to call it copy, but I'm not limiting myself to have 3-letter names, so that's not different bad. That's not that bad. So we're gonna have copy register to register, copy literal to register. We're gonna have copy um copy memory to register. I'm gonna have copy register to memory, which is a store actually. But wait, yeah, that's what we'll do. Alright, so first one we're gonna do is the simplest, which is copy register to register. So copy register to register. This now means because we have multiple types of the same instruction. This now means that we have to somehow encode what we have to encode what each of these types actually is, right? So we can simply do this by having the first 2 bytes of the instruction. So the first 2 bytes of the arguments that we're actually trying to get is is type of move, right? So the way we're gonna find out which type of copy we're doing, we're actually gonna rename this to copy now. Copy, copy, copy. So most of the time when you're getting like opcodes, it's mostly just like most of the time when you're decoding instructions, you're doing a lot of bit shifting so you can get specific elements of a byte that you need, so that you can tell which bits are which, what you need to do to actually execute the instruction, and what data you're executing the instruction on, right? So type of copy is we said the first 2 bits after the opcode is going to be what type of copy it is. So because of this, we're gonna do instruction. We're gonna bit shift it to the lowest bit, which would be bit number 10 in order. So that means that we shift it by 54, sorry. And then another thing you also have to do pretty commonly here is you have to do masking, right? So now we've bit shifted it, we have to mask it so that we only get 2 bits. Because otherwise we're gonna get the whole instruction and we only want the first 2 bits, right? And um in hex 2 bits is represented, two fully colored bits is represented as 3. Because um you have 0, 1, 1, that's 2 bits, which is 3, and obviously in hex that's just 3. So we're getting first 2 bits is 0x3. So that should give us the first 2 bits that we need. So we're now gonna switch on the type of copy. First type of copy we're gonna use copy register to register, and this case is so the first case is when it's 0, 0, right? So 0x0. And that means that our copy register to register is simply we just find so now we need to encode the data in the next 2 registers, right? So for the copy register to register, um we have a lot of space in our instruction, which means that we can actually just like store, since there's a lot of space in the instruction, we're gonna have a lot of empty space at the end, right? So what we can do is we can store at the end of each register, at the end of each instruction, sorry, this instruction, if it's of type copy, then you know that you can just do um let's call it dest reg, and our dest reg is going to be encoded before our source reg. So we're gonna shift it to get rid of the source reg, which is at the bottom. So if you want to visualize this, okay, um, control minus. If you want to visualize this, first 8 bytes, eight, you got opcode, right? And the second 8 bytes is well, actually, in computers they store bytes. This end would be byte 63 and this end is byte 0, right? So over here is byte 50 minus 8, that's byte 55. This is byte 55. And then no, it's not byte 55. This is 56. Yeah, that's byte 55 or 56. No, this is byte 56. So from byte 63 to byte 56 is your opcode. Then a single byte, which is at byte first 2 bytes, which are byte 54. So 56 to 54 from 50, 55 and 54. So these two 55, 54 represent the type, whether it's copy register to register or copy literal to register or whatever, right? So that's what this is. And then you can, and now that we've done that, we need to get at the end, since we're gonna have a lot of dead space here, basically up to around bytes, up to byte 54, like 40, up to byte like 8, I think. Yeah, up to byte 8 is gonna be unused. in this form of the instruction, right? We'll use it when you're doing literal to register. You're gonna end up using most of this for the literal, which you'll see in a second. But in register to register, it's unused. And then this last one from 8 to 5, or like from 7 to 5 actually. Yeah, from 7 to 5. Oh, no, wait, no. Yeah, seven from byte 7 to byte through 4, and then from byte 3 onwards. So byte 4 is byte 3 to 0 is a source register, and to th- um byte 7 to 4 is your destination register, right? So in order to get this section, we have to get rid of this bottom part. So we have to shift it right by 4, and then we have to mask out these 4 bits, right? So let's do that. So that means that we should be able to do 4, and ampersand that to get to get 4 bytes and 4 bits, sorry, which is F. And then we're gonna do the same thing to get the source register, except now, because we're only getting these bottom bytes, we don't actually need to shift this. So we can just get instruction 0xF. Right, so now we have the index of our source register and the index of our destination register. So now all we need to do in order to copy from register to register is we can do registers.local set. You can set the dest register to be source register. And that's that. So now all this instruction does is we get our first copy of the instruction. We first tell that's the copy instruction by going to opcode type. We then get uh um we check what type of copy it's going to be by masking out these 2 bytes. We then switch on whatever type these 2 bytes are. So far we've only done one case, which is copy register to register case 0x0, which is of the type copy register to register. We get the destination register by getting rid of these bytes by shifting it to the right, and then getting destination. And then we get our source register by just simply masking out the bottom 4 bytes here. Bottom 4 bits, sorry, I keep saying bytes, my bad. And then setting the register, the local register with index dest reg to the register with local index source reg. And the way we can actually get that is we can do what I've done so far is actually add the index, which is not what we want to do. We want to do registers dot local get, and then we want to call that on that. So now this actually stores the value. Now this is index source value. Now that looks proper, right? Index source value. Right. Cool. So that's how you do register to register. Right. Now let's move on to the case of literal to register. So we copy literal to register. So literal to register is obviously so far our encoding for literal to register is now 0, 1. And now this space that was previously unused is going to become pretty useful, right? So I still think I'm gonna prefer to store the actual register at the bottom of the instruction, right? So we'll say the bottom 4 bytes, so these bytes are still the destination register. Actually, this might need to be more than 4 bytes, you know. Now that I'm thinking about it, we also have, yeah, we actually do have these. Yeah, this is probably gonna need to be more than 4 bytes. Um, okay. I've just now realized that because we also have these 5 registers, each register index is gonna have to be hmm, um oh, that's that's really annoying. We can just load them out local registers actually. You know, we're fine. Hmm. So now the problem is that I've only accounted for the fact that there are 16 locals, but I haven't accounted for actual global registers, which is not good. Um, let's change it so it's still 16, 16 total registers. You'll have in memory, you'll have 10 general purpose registers, and then 0 to 9 and LF. Yeah, that's fine. Okay. Yeah, no, that's perfectly fine. All right, so since you just had to quickly reduce the register count because I just noticed that there would be too many to encode, and encoding it in 15 with 5 seems just like a bit of a waste of space. So yeah, okay, yeah, that makes more sense. And then for local get, I wonder what we're gonna have to change here for local get index TL. With this you can technically access. Might just have to do register get in general, and then register get, and then whether it's local or not. If it's local, hmm. No. That's fine. You know, yeah, we're probably just gonna have to have. We'll set this to be private, right? If let me just quickly check something. Um, Odin. Yes, yes. So you said to be slash plus private, just so that we can hide some of these low implementation details, and it will make this public. Public. Mm. Yeah, and then we should be able to get it with whatever index it has. So what we're gonna do is we're gonna have in here, this will be encoded as yeah. Alright, so I'm just quickly deciding how we're gonna encode each of these registers. So that's one. Um, that's two. That's three. That's three. Actually, I saved that wrong. But zero. And that's register four. Yep, that's register four. And then this starts. I will show 111, and then can go up to that, and then that's yeah. And then here the LF register is encoded as the final register. Yep. Right, that should be perfectly fine. Using 4 bits. Right. So I'll just quickly change the system so that we can actually encode all of this in 4 bits instead of having to add an extra bit, which would make this um a lot more unnecessarily cluttered, right? So I think that's how it is. Yep. Okay. Sorry for the quick detour, but that's how we're gonna encode that. And then in our get function, we'll just have it's gonna be some ugly code. If index is greater than we're gonna change this to be just a general thing of registers where it's a dynamic 64, and then you can just do we'll just have some constants that yeah, that's fine. Actually. Yeah, that's perfectly fine. Yeah, so quickly just changing the system so that instead of having a separate register of locals, instead of having a separate array of locals, we'll just have general a general array of registers. And then the first set of registers, um first set of registers is first set of registers is the global registers. So that's GI, GS, GB, GR, and GL. And then the is next set is 5, right? So that means that now that's still fine. So yeah. So now we can do local. Yeah, that's perfectly fine still. And that just means now we return registers index plus GL plus 5. You might wonder why I don't just make a GL start at 5, but that reveals like implementation details which the user doesn't need to know, right? So I've quickly just fixed the VM or the registers in the thing. Or at least I think I fixed it. I don't think that's actually how you fix it. Local. Yeah. Okay. So we can do if registers if index is than less than or equal to GL, then we'll just make it so that it returns registers index registers index plus index. Yeah. And then if it's not less than GL, then we'll add GL and then plus 5. And then here we'll have if index less than or equal to GL, then we'll make it so that registers else registers index plus GL. Now, if it's less than GL, then just mean it registers the index value. Else, yep, that's sorted. Okay. So quickly I had to fix the get and set function because at the moment it was a bit messed up. But now we've changed it so that we're just gonna make this private because I don't want people to just be randomly touching this. So we now have a dynamic array of registers. Actually, don't make it private. We have a dynamic array of registers and some predefined indexes for GL and GS and GB and all these global registers. And now, for our get procedure, we have if the index is less than or equal to GL, then we return the value of index. So that will just give you the global registers. Else, it'll return um GL plus 5 so that we don't end up touching any of these global registers. And similar thing happens here where we set the value of the global registers if the index is less than GL, and if it's more than GL, then we just set the value after, right? All right, so after that quick tangent, we've now fixed that. We'll do registers dot set registers dot get. All right, so assuming we wrote that correctly, before we actually add any more instructions, I'm actually going to test that this works because that took me on a severe detour. We're also gonna um, reserve in registers. We're actually gonna registers. Give me a second. Yeah, we're not reserving. We actually have to resize. So we'll resize this to be like we're just gonna make this actually. Because actually no, we'll resize that and then we'll resize that to be like I know we'll free we'll defer delete memory. Resize that to be like let's just leave it at 1024 and defer delete registers. Yep, okay. So now that we've done that, not a reference, we need it to be the actual thing. So now we've done that, we should be able to just like assign variables at wherever, right? So what we're gonna do is we're just gonna have a template instruction that's like so 0 at the first location, which should be where this starts off, since all data is initialized to 0. We're gonna do we're gonna set first of all, we're gonna do registers. We're gonna do a bit of a cheat here. We're gonna do registers set not registers set registers um let's just set like 6 or something. Set register, set the first local, which is at index like 0x 5. Set that register to be um register 5 will be set to, we'll just set that to be like 20 or something. Then we'll do registers dot get 0x5. um for this test, we're gonna immediately, want the first time it's run, we're gonna stop, and then we're gonna print out. Okay, then we're gonna set register 6 to a value 0, or it should be nothing actually, but so essentially we're gonna test that this instruction that we've written actually works, right? So we're gonna do registers dot get 6. So we are going to set at memory 0 is equal to registers, no, is equal to this hex, that this binary that we're gonna write, right? Actually, no, we're gonna write it as hex so that makes it easier, right? So the opcode is 0, so that means that the first byte is 0, right? For reference, each character in hexadecimal is 4 bits, so that's a byte, right? So now we have our opcode, which is 00. Then the next byte, next two bits are what type of instruction it is. So we need to set the top bits of our of this nibble. So the top 2 bits of this 4-bit byte that I've set here to be 3, right? So this should be, so next instruction. That should be, let me actually draw this out. So if you want to set it to be 00, oh wait, we can just set this to 0. I'm silly. If you set that to 0, we set all of this to 0 actually. So first byte is 0, second nibble, which includes this, is also 0 because we are doing the first type of the instruction, so that's 0. Then all of this up until 7 is 0. So up until the last 2 bytes is 0. So that's 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes. Right. So now we've done 1, 2, 3, 4, 5, 6 bytes. And now in these last two, in this, actually we only need one more byte, 7. So in this last byte, I'm gonna send the first nibble. So we're gonna set the first 4 bits to be the first 4 bits. These first bits, if you want to get register, destination register is 6, and our source register is 5. So essentially, if we split this up, I'm split this up and now I'll recombine it, right? So this is the opcode. Then this is the type of the instruction. Since we only have one, this is 0. That means that this is destination register. This is copy register to register. Then all of this up until here is unused bytes. And then 65, 6 is the destination register, and 5 is the destination. And 5 is the source, sorry. So if we write all of that, And now, assuming that we wrote this properly, what should happen is we set register 5 to be 20, and in our memory we've added an instruction which says copy L0, copy L1 to copy into L1 L0, right? So register 5, you can see here like that. Register 5, as we said earlier in our encoding here, L0 is 5 in bit. This is 5 in not no, actually that's not 5. That's 5, right? So bit 4, so that's 4 1 5. So that gives you L0, and then L6, and then L1, sorry, is encoded as 111 as 0110, which is 6. Right? So what should happen is you should get the instruction, run through this. It should copy the value in the source register into the destination register, and then print it out, and the program should stop. So I actually haven't opened a command prompt yet. Let me open terminal, drag that up here, go to desktop programming, Geppetto. I can do Odin dot dot slash Odin build run Jep VM. And of course, we have actually not properly set this. So registers, we actually meant to delete registers. That's what we meant to do. And then, yep, that's like that. Give an argument. Use of import registers, not like that. GI. I think I called too many things registers here. We're gonna rename this to memory. Rename that to memory. Can't find registers Odin, obviously, because I just renamed it. No. Memory. Rename that to memory. And that to memory. Wait, no. Yeah. And then we can just move our memory from out of here into memory. Use 4 like that. And now that means that we should just be able to go here, call that memory. Then we can just do memory dot memory dot memory memory memory. I'll rename this properly later, but for now, just to get it to work, let's quickly rename this dot memory. Oh no, that wasn't a problem. I actually didn't need to do that. Let's actually rename this back to registers. I actually didn't need to do that. That's a bit silly of me. Rename registers. Cool. Don't save that. Yep, okay, yeah. So the actual problem was if I go to registers like that, registers, and then I go here, what I meant to do is I meant to go registers get, and then we can get this value in registers. So now what we should be able to do is use of import registers without selector. Do registers dot set g to be register dot get gi. gi plus 1. Obviously, this code has now become a little bit more complicated because we've had to abstract out this registers, but you know it is what it is. It will make other sections of the code more simple, right? So now, proof that our instruction is working, we've actually got the value 20 printed out, right? So we did this. It was actually pretty simple. I just made things a little bit more complicated in my implementation. But other than that, as you can see, the main loop that you do is you load your file into memory, you loop over your instructions, you get the opcode, you execute them, and the way you execute them is you get bytes from them to find their arguments, and perform operations based on those arguments, right? So I'm gonna go on a quick little break now. Gotta go do some things, and then we'll be right back continue implementing um to continue implementing some more instructions and also having a look at some management strategies for how to actually implement this. So I'll be right back. All right, we are back for the second half of the live streaming programming a virtual machine. And so today, in the second section, we're gonna quickly go over this, which is a way you can speed up how you loop over code, right? So this is a technique that I was originally considering using in this VM, but knowing what I know now and the way um the way this system works, it's not gonna make too much sense for me to do that. So I don't think I will actually do that. But it's still a very interesting thing to know. So what we're talking about is threaded. Let me just actually remove that. We're talking about threaded code. So threaded code is hmm, if you look at the code we've written so far for the VM, um, every time we get a new opcode, we decode it, we go to the end, and then we go to the top again, and we go to end and go to the top again, and we keep looping, right? So that's the way that we presently do it, right? However, um, this looping back to the top can be seen as an unnecessary step when decoding and executing your instructions, right? So you have each instruction, you go to the bottom, then you return to the top, sort of like this, right? So you have your switch statement, this switch, which goes down to our copy instruction, which then goes back up to switch statement, which then goes down to the next instruction, which would be like add or something, and then goes up to the next statement, and it keeps doing that until the program terminates, right? So, the theory behind threaded code is that you can actually eliminate this return step. So instead, you can just go down. The theory is that you should just be able to, instead of going down and going back up, you can go down like this. So like you're in your main loop, main, you go down to your copy like this, and then the copy then goes down to your add, which then goes down to your move or to your load or whatever, which then keeps going down, and eventually once you've executed all of your instructions, you go back up to the main loop. And this is better than having a switch loop where you're constantly going back and forth, right? Switch, and then you're going. All right, so that's basically what this is trying to explain. So instead of going back forth and back forth, we're saying that in theory this is faster, where you go from the main loop, you go down to copy, then from copy you go down to add, then from add you go down to load, and you keep going through all the instructions, and then eventually you get back to main, right? So that's called what threaded code is, right? And there's two primary ways of implementing threaded code. You have direct and you have indirect, right? So with direct code, the way you achieve what we talked about here is you make each instruction a function pointer, right? Inst f p. So that way, essentially what you can do is in our system, for example, you do something like um registers. You do something like you'd get register dot get registers registers gi, and then you'd what you do is you get this, and then you dereference it because the value you get is a function pointer, and then you run it basically, and that's how you would run it. Now obviously in our system we can't do that, right? In our system we can't do this because each instruction, it's not that the instruction is only holding the function name, it's also holding data as well. So we actually can't do this because our instructions hold data as well, right? So that means that we can't do this. So that means the other option is um indirect function calling, which means that instead you still have opcodes, but each opcode indexes an array. um, op it indexes an array of function pointers instead. So it indexes a function pointer array, which then points to the actual function. Now in both of these methods, what then ends up happening is that essentially the function that would be like let's say f functions or something, you got functions register gi whatever, and then that calls that, then that actual function, so let's say like it would be a copy function, this copy function up here would then return, no, this function wouldn't actually return. It instead, what it does is it calls the next function. So it would have this function, it would have this thing, and it would call the next one. And then essentially we've replaced this entire loop with a bunch of functions that recursively call each other next, right? So we could do this, and if you do it in assembly or if you do it in C using go-tos, which I might link to in the description, if you do that, it works really well, and it's a lot faster than jumping back here doing that all over again. However, because we're writing this in Odin, and because also it makes the code less readable, because obviously if it's in assembly it's definitely less readable, and if it's in assembly it would definitely be less readable, and if it's in C it uses go-tos, which is a bit weird, and like go-to labels and all this weird stuff. um it doesn't really make sense to do this in our system because the switch code is cleaner. Switch is cleaner, and it's the speed loss from this is made up for in most systems. So while direct threaded code is really interesting, um it's not a practical technique for what we're doing. So it's not too slow. Right. So we've gone over that. So now let's get back to implementing some instructions, right? So let's go over to copy, right? So now, when we left off, we're working on the next instruction, which is copy literal to register. So copy literal to register as an instruction. Let me just quickly check this. When copying a literal to a register, the way we want to store this is as follows, right? So if we hmm, let's go over here. So lit to reg would look something like this, right? So at this end, once again, we have byte 63. At this end, we have byte 0 with bit 0. Sorry, I keep saying byte. And then, so from 63 to 56, once again, we've already established that from 63 to 56, that's the opcode, which is the same as before. So we can ignore that. Then obviously this is now different. So the type of copy is now different, and it's now 01, which means copy literal to register. So what we can do is now we need to figure out how we're actually going to store literal to register. So I think I talked about this in the first half, but essentially, um, for simplicity's sake, and because I think it'll allow us to get the maximum amount of data that we can, right? Um, I'm gonna store register data in all of these instructions at the end of the instruction. So instruction here, this will be the destination register, right? So bytes 0 to 3 is destination, and then by 0 to 3 is destination, and then all these bytes is an immediate value, which is the literal, which is so all these values are the literal, which means that we've used up 8 bits here, 10 bits, 4 bits. So we've used 14 bits here, 14 plus 64, 50-bit value, 50-bit value left. Although it's probably simpler to just leave it as a, but yeah, well, 50-bit value, right? So now that means that we have a dest, we have a lit 50, which means that we just need to shift this to the right by 4 and then mask out 50 bits. So instruction is getting shifted to the right by 4, mask out 50 bits. 50 bits represented in hex would be, that's 4 bits, 8 bits, 12, 16, 20, 24, 24. You can copy this, 48. Um, and then to get the remaining 2 would be 48. And then to get 2 bits is 3. So this basically represents 50 bits. So now we've got a literal value of 50, which now means we should also, just for safety, actually no, that's fine. And then we can then get our destination index, which is these bottom 3 values. So that just means we can do inst. Yeah, nope, not that. XF. So now we have this, and we should be able. So we have this literal, we have this destination register, And now all we need to do is we can set dest index source val. Not we can set the thing at destination index to be lit 50. Okay, so now we're gonna quickly test this. We're still only executing one instruction because that's how I code it to function for now. We'll then do same instruction. This time we go here. We want the first bit to be 1, so that means that this nibble, this 4-bit is 1. Then the dest reg is register 5. And now all of these bits left over, if I'm looking at this correctly, um, yeah, that's 8, that's 10, that's yeah, all of these bits left over can be whatever we desire them to be. So we'll say no. Actually, I need to set the upper values. So if I need to set the upper values to be, see, this is what's weird about writing hex, is that we want the high bits of this to be 0, 1. So because each hex character represents four um four of these, that means that if we want what we want, because that means that this is 56, right? This value here is 55, and this value here is 52. So now what we want is we don't care about these two. We want these to be 0. We want this to be 1, which means that we're saying the high bits, right? So these are this is the high byte. You'll see this in reference manuals referred to as the high byte, and this is the low byte, right? So low byte we want to leave as 0, high byte should be 1, right? So this is so if you look at this, this is 4 in binary, which means that if we want to encode this to have 1 in in the lower high byte, if we want it to encode 1 in its high byte, we have to store it as 4. Now let's choose any number to just store as a number. So we'll just do like 256. So what this should do is opcode 0. High bytes here is 0, 1. So that means that we're choosing our literal reg, that we've chosen our copy literal. Um so yeah, so the high bytes of this is 0, 1. And the low bytes is 0, 0, which means 0, 1, 0, 0, which is 4. So that means that it's a copy lit to reg. Then this is our literal, which is 256. And this is our destination register, which should be L0, which is encoded as 5. Right. So I'm gonna just write this is L0, copy L0 5, right? And now what should happen? Should get this, and now um assuming our programmers work properly, it'll decode it, see that this is 0, 1, see this right register, go to the right byte, and then now we should have it should get this literal from the right thing. So it should get this correct literal. It should it should get the destination index from the bottom, and it should set the destination register to this lit 50, putting 256 in L0. So assuming we did all that correctly, go here, we can do Odin build run jet VM, and it's printed 0, so we've done something wrong. Hmm. Hmm. So if L0 is encoded like that, oh wait, is it minus? Oh, okay. I think in my registers that might be wrong. Let me actually verify that. So that'd be 10. If I do that as A, okay. Hmm. This is a great time to back out or to showcase the debugger that I like to use, which is really good. It's called Remedy BG. Um, People watching this probably know what it is, but it's a really good debugger. If I can find where it is, where I left it, I forgot where I extracted it now. Oh well. Um, just put it on my desktop. So just go on my desktop. That's extracted. Is all that. So Remedy BG is a really good it's like a really great debugger in comparison to like Visual Studio debugger. It's basically the Visual Studio debugger but runs at a speed that isn't horrible. And so you should be able to save that to JEP as JEP VM RDBG. It's like a really good. I might link it in the description, right? So I actually need to rebuild this to build with debug flags, and then now if I run, I do fn5 exit with a code of 0 obviously, and then I do f10 f10 let's go through here. Let's click in this. Let's F11. F11. No, wait, no. F10, F10, F10. F11. That's what I want to go into. F10. Okay, wait, Shift F5. Let's go into here. Think. Yeah, it's here. That's where it is. We do FN F5. We do F11. What is that? What did I just do? No, F11. There you go. Cool. Yeah, we go in here. We do an F11. And cool. Now we're here. Just quickly put a breakpoint there. And let's go here. I will do F5. So now that we're here, let me actually zoom this in. If I can zoom in, I think I can zoom in. Window. Might not be able to zoom in. Anyway, so we'll go through the motions. So it gets our instruction. So we're gonna need to know some of our instructions. So our instruction, we're gonna need to know our opcode. We're gonna need to know we're gonna need an opcode. We're gonna need to know the type of copy. We need to know lit 50. And we're gonna need to know dest index. Not dest in there. Dest index. So if you go into F10, step through, you've got that instruction. Opcode is still copy. Step through, get the type of our copy. And there is our problem. It has chosen the wrong type of instruction. So it's probably a problem with how I've actually typed this out. So, okay, if you want our top 2 bytes to be, hmm, let's actually go through this on a binary to hex converter so that it's a bit clear. So, our binary number, if I open up Milton, put down the side, put down the side. So if we look at this, binary number should be our first our opcode, which is 0000000, then 5601. Now our literal should be our literal should be zeros, but with the last um with the should be 50 should be, yeah, it should be around should be 42 zeros followed by 8 ones, right? So 1, 2, 3, 4. This might make more sense to do here. So if we swap, we enter our binary number. So if we look at this, what we should have, top 2 bytes F is 00 to get 00, obviously. Then this represents 4. So bottom 2 bytes is 0. First byte, the top 2 bits is 01. That then means that the total number is 0100, which should be 4. Then the literal is, let's see how this converts first. Convert. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's our opcode. And then it's 50, 56, 50. Yep. And that is, yep. Okay, so that's correct. And then, so maybe I've shifted it incorrectly. I might have shifted it incorrectly. But that should theoretically be correct. Now, I've stored the wrong. That's why, probably. F, F, F. Let's do it like that instead. And then we'll Odin run JetVM. Filter link. Obviously, because it's still open in my thing. And then we can go here, rerun JetVM. It's still 0 because I'm starting to think I might have bit shifted this incorrectly. So let's first verify that that's actually the problem. See, Control V. Let me actually change that to be 0. And I could do that and then convert. So first 8 bytes are um zeros. So first, that's our correct opcode. And second, yep. Third, yep. That means that these bytes should be not FFFFFF5. We just want convert. Yep, like that. And it's 01 twice. So all this go down to here. Yeah, so we can look at this here. And then, so first four is is zeros. Then these two, 01, 00. Then the rest of it up to around here is 256. And then this is 01, which should be the right register. So yeah, so I've written the right opcode. So it's definitely a problem with how I've shifted this. So if I go to Remedy BG and I check and I run up to No, it's the wrong thing. I need to rebuild actually. Build debug. Fn F5. Yeah, don't need to do that anymore. Fn F5. Yep. So now go through the motions. That should give us the same number that we got in here, and it does. Then our opcode should be 0. The type of copy we do is still 0 because the bytes that we've chosen to shift apparently are incorrect. So maybe it's 53 that we need to shift, or maybe it's 50. Maybe it's 53. That might be it, but it probably isn't. Yeah, obviously, because I haven't closed it properly yet. So F5, run that. Nope, I still don't. Okay, shift. Will this stop? No, shift F5. Am I like, okay. Control, stop. That's what I was looking for. Simple operation. Huh? Yeah, so it should have stopped, but anyway. Next. Okay, this is just bugging. Now I gotta close this. Save the changes. Now rerun it. And it's still 0. So, in order to get these bytes, right? 3, 62, 61, 60, 59, 58, 57, 56. Yep. And then 55, 54. 53. I already changed 53. Why is that wrong? Yep, that's like that. And then this is really odd. Like, I'm not sure exactly what's going on to make it do this. Because it should be shifting. Okay, if we go through it, we shift 4 to get rid of the 5. Then we shift 12 to get rid of the FFF. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 zeros. So then we should shift. If you should shift 36 spaces, that's 48. And then, oh, so I've shifted the wrong amount. So shift 50. Only run jet VM. Now that is not correct. And then I've gone too many bytes, is it? So if I copy this, paste this here, and just type it as that. That's a 3 front. Yeah, that should be a 3 at the front. And then F, 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 F. So that should be, if I put that into my hex converter, that should be 51s, but 51s and then 2 just zeros at the top, which we don't care about. So one, two, yes, 48 digits. Wait, why is it 48? Let's do FF. Yeah, it says 8. But we want 50. So if I do F, no, still 48. FFF3. Yeah, okay. So I need extra F here. And only run jet VM. Hmm. 12, 16, 32, 40, 50. Yeah, yes. Right. Okay. So we're masking out the right number of bits. So it's 8, 16, 24, 32, 48, 50. Huh? 16, 32, wait, 16, 32, 48. Yeah, 8, 16, 24, 38, 24, 24, 32, sorry. 40, 48, 50. 8, 16, 24, 32, 40, 48, 50. Yeah. So why is that? Huh? Is it because we're no, no, but hmm. So why is that lit 50 being represented like that? This is where having a debugger is very useful. So we open this. All right. We open JVM. So go over here. Hold in debug. And now we no, I already have a session, sorry. Open no JVM. Yeah, we got that. And then now we should be able to just stop at lit 50 and then F5 FN F5. Yes, we're at lit 50 and F10 F10. So now lit 50 is that. Huh. Yeah, so we've gone the right register, but we've gotten the wrong value. Okay, so if I were to just mask out FF, if I were to just mask out FF, and then I shift F5, and I run JetVM like this, yeah, so I got the right value. So we got 255. So that means that the masking itself is working fine. Problem is we're masking the wrong number of bits, or we're not getting. So what should happen, you should mask it out like this. Okay, let's see what happens when we leave it at 0, right? So let's run RVM and mask out 255. So what happens if I mask out the next bit? Still 255. Next. Uh, next. Yeah, so if you, yeah, keep going up. Oh, so you were just masking the wrong number of bits. Okay. So now we should be asking the right number of bits. So 4, 8, 12, 16, 24, 28, 32, 40, 44, 48. And then that's the bottom two bits. So that's 50. Cool. So now we've implemented a literal copy to register, which takes in a literal value that can be up to 50 bits long, takes in a destination register, which is at which is the following which is the last four bits in the instruction, and then it sets the destination register to lit 50. Cool. All right. So now we're gonna think for today. Since I don't have too much time, we'll implement these two instructions, and then tomorrow, hopefully, we'll go through. Um, we'll add some control flow instructions, some arithmetic, and we'll go over some IO tomorrow. But let's get back and implement um 0x2, which is 0x2 and 0x3, which are movements into and away from memory. And then case is just invalid, so FMT um invalid copy skipping, and that skips over it. And this is copy copy memory to literal. So this one should actually probably be simpler. So we should be able to do lit 50 should be able to do. So if we're looking for how we're going to lay out um this instruction, we'll have once again. So now we're doing mem. Now we're doing memory to literal. So now instead of one, it's two. So now we have this. Instead of having a literal, we are going to have a displacement of memory, right? So this is once again 50, and then we obviously have our destination register at the end. So this is actually very similar to our literal copy. So we can copy this, copy our literal code over to our memory code, right? So just actually say just register to register. Yep, like that. Then this now is disp 50. Now, because we can only displace using 50 bits, that means there's a whole 14 bits or like and sections of memory that we simply can't access. So that means that the best course of action to do here is to actually base hmm, I could introduce another register, but I feel like that would add unnecessarily complexity. So what we're gonna do is obviously we've got our displacement 50, we've got our destination index, And the way this instruction will now work is we are going to have, let's just set desk index to um registers 2. So we want to get the actual memory at the location, right? So memory, it's called value is equal to, so we index into memory, and we're gonna do what's called a memory displacement, because obviously we can't reach addresses that are bigger than 50 bits. Although typically you're not going to need to do that, but it's still pretty useful to do that. So we can then set our base pointer to, the base pointer is I think I've actually misexplained what a base pointer is now. This is, no. This is a base pointer holds the address for displacement. That's what this is actually is. And bottom of stack, I think, can be both, but it's mostly for displacement, right? So essentially, in order to access higher regions of memory, we're just gonna add this 50 address onto our registers, get registers dot gi, no, gb. So again, our base pointer, and then we'll add that to um displacement 50. So now we're getting, so the value from memory we're getting is the value at location display 50 displacement 50 plus the base pointer. So whatever the base pointer is, you can then displace off of that in order to reach more memory, which is obviously why it's initialized to 0, so that when you normally just call this instruction, it just gets the actual literal address of the memory. And now we can just set that to be the memory. So now should be able to go here. This is now, instead of 0 1, it's 1 0, which means that the top byte is so now it's 1 0 0 0 plus 1 0 0 0. That translates to 8 in binary, right? Which means we can just put 8 here. So now we've got our opcode value 8, our displacement literal, which should just be ff, so 25 and then 5, right? And then yeah. So how you write this in the actual assembly is you'd probably write it like 0x ff, right? And then in memory for this test, we'll put at that memory location the value of 255 or like 207 or something. So now that's at this location in memory, and now you should just be able to access it like that, and we should print out the value at this location. So if you do only run dot, and this one worked perfectly because we figured out the literal. So we figured out how to get 50 bits, so now it works perfectly fine. All right, so now we're gonna implement 2 more instructions, and then I'm gonna go and we're gonna have a nice time. So for the next instruction, which is the final one we'll implement today, no, second to last one, penultimate instruction we're gonna make today, is register to memory. So normally in other systems it's like a load instruction, right? But I've just decided, we might as well just put it all in one instruction. So register to memory is simply register to memory reg to mem. So now register to memory is the final instruction we're doing, and that should be erased, and that should be 1 1. so that now, so we first have our first 8 bits are the opcode, second 2 bits are 1 1 to indicate that it's registered to memory. Then we have our displacement, and this time instead of a destination reg, simply a source reg. So now we'll do the final. We're in the final stretch now. Just gotta copy this code again to get this. And so now we have our displacement 50, our dest index, which is not the dest index, it's actually the source index. And now we can do memory at we'll create a variable called index because it's simpler to do that. Index equals colon equal to registers dot get registers dot gb plus disp 50 memory at index is now equal to registers dot get source index. And now we should have a similar functionality. So now um 00 is the opcode. F is the since we now have it as, oh no, since we now have our thing as 1100, it's actually not F, sorry, it's 12 because top byte 4, so it's 12, and 12 in hex is C. So C, then 5FF, which is still the memory location, then we have there. So now we should be able to do registers dot set. We'll set register. We'll set the fifth set L0 to be um 341, and then what we want to do is we now want to print the memory at 0xFF, and now this should work. Only run JetVM, and we worked again. So, as you can see, we obviously had some trouble with this literal register. We had a bit of trouble with how we were structuring the actual register system in general. But as you can see, with virtual machines, once you get going, it's actually relatively easy to continue going, and it's like pretty simple to continue working, right? So as you can see, my computer's gonna die soon. So we're gonna implement one more instruction, and then we're gonna call it a day. So this last instruction is not a data flow instruction. It's actually an add instruction. So we're gonna add. We're gonna make an add instruction, and this add instruction is going to. So let's look at how we're gonna structure this. So for the first time in a while now, we're actually gonna have a different opcode. So now our opcode is opcode for these first 8 bytes is right now it's 001, although that's not actually what I want it to be. But we'll have the opcode is 1, okay? And then zeros following it or whatever. So right now opcode is 1. And opcode is 1. And we don't have multiple types for this instruction. Although I might make it multiple types for addition, multiplication, and division. Well, that might make sense to make those all separate instructions, but we'll see how it goes. So we have 2 forms of this instruction: register to register and literal to register. Right. So what we're gonna do is we're gonna implement both today. So for register to register, It's very similar to our copy register to register, except now um we're adding the values together. So destination and source, and this is unused. So we take our add instruction, we get our dest index. Our destination index is at inst 4 0x f. Yep. And now our source of value is equal to registers dot get inst 0x f. And now what we should be able to do is we should be able to write registers dot set. We should be able to set um the value of our dest index to be registers dot get dest index plus our source value, which basically just adds our value to it, right? So that's how we're going to do that. One thing I've just now noticed is that we actually are going to need um a multiple types, but this one, it's only going to be a 1 bit for the type. So we're going to have 1 bit, and that bit simply tells you whether it's the literal form of the instruction, or whether it's the register to register form of the instruction. So with the literal, this one is the register form. So we need to shift this by 55. Actually, to shift our add instruction, type of add is equal to instruction shifted 55. Instruction shifted 55. And then we only get 1 bit. And then we're going to switch on the type of add case. If it's something else, then we'll just do fmt println invalid add skipping. Then we'll do register and register. For 00, the add is register and register, and we can just put this code in here. And now we can do the second version, which is literal and register. So our destination register. So we'll get our destination index from the end. So our dest index. So for literal and register, obviously, once again, this is now 1, and the last nibble, or the last 4 bytes, is the destination. And then now this is a lit 51. Lit 51. So one thing that we do need to note about this about lit 51 is that okay, so we support we're gonna support signed numbers in this system, because you kind of have to for a lot of different like systems, right? And one problem you may notice is, how are you gonna represent signed numbers if you've been using U64s this whole time, right? So we're using something called 2's complement. So 2's complement. So 2's complement is a um. 2's complement is a is a way of representing signed numbers using binary, right? in computers. So the way you can do this is, for example, let's take the number 6 in binary, which is 0011 0 sorry, 0110 is 6. So when it's not, oh, wait, no, no, wait. Yeah, so let's say we have this 4-bit, we have this 4-bit value 010, right? So in when it's not two's complement, um when you're just treating this as an unsigned number, this is this position is 8 and this position is 2, so that's 10. However, it's also minus 2. How? Well, that's because if you look here, so the top bit in this representation is the sign bit, right? So we'll call this S. So the top bit in this number is the sign bit when you treat it as a signed number. And I gotta be quick with this. The top bit is the sign bit. So obviously we trying to think about how do you explain this. The top bit's a sign bit. So when this bit is on, we're in signed mode. We're treating it as signed. So the way this works is essentially, in order, the way you figure out what this number is via its sign is that you can I actually forgot. I'm not. It's kind of embarrassing actually. I gotta search this up on the stream. I'm trying to remember how you explain this. But essentially, what you do is you flip every bit and then you add one to the whole inverted number. Okay. So essentially, take all of these bits. So this 8-bit is now minus 8, right? And this is obviously 0. So this 8, hmm, these are two. So we're gonna flip all of these bits. So that should be so now the number is 0101, which is 5. 0101. So it used to be 10, now it's 5. Now what we do is take these we take these two, um and we add 1 to the whole total. So wait, is it, hold on. Hmm. Yeah, so you add 1 to this value, which gives you, so plus 1 to this is 6, which is 0110. Right? So this is actually, I actually said that's wrong. That's actually wrong. So that means that this is now 6. So no, what? This is how you. I've represented this wrong. Let me think of this. Hold on. Sorry. I'm actually very sorry. I'm trying to figure out how I properly explain this. So the point is that two's complement is a way of representing, um, signage in computers which don't actually support a way of representing it, right? So if we have a number, like, if we want to turn a number from a positive to a negative, positive to neg, let's say we have the number 0110. So that's 6. So that number is 6, right? Equals 6. And then In order to turn it into a negative number, we first flip all of the bits. So that should be 1, 0, 0, 1. So now we flipped all the bits. So we flipped all the bits. So now every 0 becomes a 1, every 1 becomes a 0. And we're left with this number. And now we add 1 to this number, which means 0, 1, 0, 1, 0, which gives us a positive number of 10. However, if you remember, as I said earlier, this is the sign bit, right? Which means that because this is the sign bit, we know that this bit, whatever value would be in this bit, is now negative. So this value is 8. So this value is at position 8. Um, which means that now, because it's 1 in this position and it's a sign bit, it's now -8, right? So we're adding now. In order to find the actual value, we obviously add all these together. So this is the fours place. There's nothing in it, so that's 0. This is the twos place, and because it's not the sign bit, you add 2. And because this is 1 and there's nothing there, so you add 0. So then -8 plus 2 is now -6. So that's how we go from a positive number to a negative, right? So what does any of this matter to what we're talking about? Well, it matters because we only have um 51 bits to represent our literal in this instance. We have to actually extend our literal to be we have to extend our literal to be the size of a U64, right? And the reason why we actually have to extend it is in case this top bit is a sign bit, we don't want to lose that signage when we expand to the top. Because normally expansion will just converting from one type to another in most languages, and I think in Odin would just keep the value the same. Would keep it not keep it the same, sorry. Would just add zeros to the front of it. But instead we want to bring that one that's at the end all the way to the front. So the way we're gonna do this is I actually have an implementation of this already in my sign extent. So we're gonna carry this, I'm gonna copy this, I'm gonna paste this here, I'm gonna explain this while we change it, right? So sign extend, it takes in two parameters, x and a bit count, right? So I'm gonna change this bit count to be, I'm gonna change the types to be 64 since we're making a 64-bit machine. So result is x. So if our result, or if x shifted by our number of bits that we care about, -1. So we need to provide the bits to know how many bits is actually being matched here, right? So because obviously we're still storing as a 64-bit number, but clearly our number doesn't match its signage because we still have these 51 bits at the base. So we need to do is we need to tell it how many bits we are concerned with, and then it takes away 1 from this bit count so that we get the top bit of the value. So if this bit count was 4, it would shift it to the right by 3, leaving us with this top value. And that way we know that. And then if it's not 0, then we want to flip all of the bits, or we want to match. What's that mean again? Hmm. So obviously if this isn't true, we obviously just return the value because it's a normal signed value, and we can just it's a normal unsigned value, and we can just add stuff to the front of it. But if it is signed, then we do an or, where or basically, if this is if one number is 0, one number is 1, then the result is 1. So we basically turn all those bits we turn the top bits positive at the end of the thing, and then we're gonna turn this into a 64-bit, so we need to times this by 4. So we get Control C, 1, 2, 3, 4. No, like that. 1, 2, 3, 4. 1, 2, 3, 4. Right, so that should be right now. So essentially, it ores this to get the to change the bits so that we get the correct signage, and then it shifts that the number of bits so that we only need to sign the bits that would otherwise be unsigned. Right now that we've done that, we can now go back here and go to our desk index, and obviously we need to get our literal 51. So our lit 51 is set to be equal to our instruction bit shift to right by 4, get bit shift right by 4, and get 51. So 51 in hexadecimal is f. If I look back here, was 50, and we can just add 1 to that. Yeah, so our literal here, control C, copy that, get that, paste it here. Yep. We can close this. Yep. Paste that. So that gets 50 bits. And in order to get one more bit, we need to increase this to 5. Oh no, we need to increase this to 7 in order to get all those bits. So that should translate to 51, right? And now our destination index is hmm, our destination index is just inst f. That's how you get destination index. And now we are going to do registers dot set guest index to be registers dot get, where registers dot get guest index plus lit 51. And now we're going to employ that function that we just made, sign extend this. So we're going to get lit 51. We're going to sign extend to lit 51 by calling it on itself. So we do lit 51 equals sign extend lit 51 by, and the bit count of how many bits is actually in the thing is 51, obviously. So now we've successfully sign extended our value, and it should now we should now hold the same value over time. And then, right, so for final demonstration to show that all that we've done today, so far we've implemented add instructions, we've implemented all this, all that, right? So we are going to we're gonna write a nice little program for ourselves, right? So at memory location, let's do something interesting. At memory location xff, we're gonna have the value 50, like we're gonna have the value like 341. Right. So now what we're gonna do is at memory 0 0, we're gonna have an instruction. We're gonna have a move instruction that moves a copy instruction, sorry, that copies copy instruction that copies the memory to register, sorry, not memory to literal, that copies the memory at, in order to copy the memory, we want to do um completely forgot what we did to get copy memory now. um Memory to register is top 2 bytes. No, memory to register is 8, so that should be, yeah, 8. So copy that, so copy 8. um this is 1 1 2, no, 2 3, 4. So yeah, so that's the opcode, that's the type. Um, Memory location is this, and we do it to 5, right? Then, so this copy should copy into L0 the value at memory 0xf. The value at memory 0xff. Then we're gonna do memory at 01 is equal to 0x 0 um x 080. Now we're gonna do a doubling operation without multiplication, right? So this is gonna be interesting. So we're gonna copy um register to reg, which is 0, and then skip all of that. And now we're gonna copy 5. We're gonna copy into 6 5. So copy L0 0x L1 L0. Now we're gonna do memory 0x2. We're gonna copy. Now we're gonna add these two registers together. So we're gonna do an add operation, which is the add operation is register and register 00. We don't need 00. No, 1 0 1 0 like that, 6 to 5 like that. Add L1 L0. Then this 0x3 is equal to 0x 0 1 1 0 1 0 1. No, yeah, 0 1. Yep, that's correct. Actually, no, it's not. No, it's not. I need the top bit. So if we only need this, that means that 1 is always 8. So that means 8 0 0 0 0. We'll add like A or something. We'll add F because I know that's 15. And then we'll actually just make this 255 so I can more easily tell what it's supposed to be. And then the registers we're adding, the register we're adding this to is 6. Register 6. Add L1 15. Then we're now gonna do one final operation, which is that we copy from we're gonna copy from register to memory, right? So register to memory should be 0x3. So top 2 bytes is that, and that means that that's 12. So 0 0 and then get 12 is C. 0 0 0, all that goes to 6, and the memory location is FF. So I should copy to 0x FF L0. Right, so 255 doubled is 255 times 2, which is 510. 510 plus 15, it should be 525, right? So what we should get, this value should be 525. And there is actually one more instruction that we need to handle, which is the halt instruction. And we're gonna add a halt, and that instruction is obviously, that means that we're gonna just have our instruction that's memory 0x5 equals 0x 0 0x 3, I think. No, 0x2, sorry. It goes all the way like that, and that's a halt. and this is printed after. That should be 525. 525. Yep, like that. And now what we're gonna do for the actual halt instruction, you do case dot halt, and what you do is you just set running equals false. Okay, so what should happen is we have 255 in the memory location. We copy 255 into register 0, then we copy whatever's in register 0 into register 1, then we add these two together, which should give us 510. We add these two together, we add 15 on top of that. I've actually stored the wrong. No, yeah, I've stored. Yeah. So which should give us 525, and then we store 525 at memory location FF, and we halt, and then now that should print out 525. This is the moment of truth. See if that works. 255, because no, it doesn't. Why does that not work? Oh, wait. Memory to register. Or is it to memory? Memory at that index. Yep. Okay. Have I copied it from the wrong thing or something? Or like 5. Huh. Well, that's not good. Is it the way I'm getting the? All right. So I want these instructions to work before we go. Before I go, so we'll write out these instructions and then we'll see how it goes. F10. No. Not F10. F and F5. Oh no, I forgot to build with debug symbols again. JetVM. It's open in here. Shift F5. Shift F5. Control. Stop debugging. Oh no. Session. Open. JetVM. Now that should stop at this memory location. You um build that. Do Fn F5. Yep. Okay, so we do F10 to step through, and we'll step in. Well, not actually highlighted. Yeah, F10. F10. Yep. Hmm. Why is that the destination index? So let me just check that we're actually that registers dot gi. Um. Hmm. No, I'm shifting it right. Why am I shifting it right? Register to register. We should not be doing a register to register move on the first operation. So that's wrong. Memory. Actually, wait, no. We'll do shift F5 and we'll do Fn F5. So yeah, we'll do that again. We'll step through. Let's go. F10. Opcode is copy. Type of copy is 0. Yeah, so it's gone to dest reg. So what is that? Which instruction is this then? No, that's wrong. Control X. Swap. Convert from decimal to hex. Control V. Convert. Yep. Yeah, no, that is the right instruction. But it's selecting the wrong thing. The type of copy is wrong, that's why. Hmm. 54. I think I've been getting the wrong type of copy. So if I rebuild, I forgot to close this. If I rebuild, forgot to still close this. Shift F5, Shift F5. Stop that. And then Odin run JEP VM 255 still, but at least now it should be building it properly. Slash dollar slash remedy bg JEP VM JEP VM .bg. Okay. This is the boring part of the stream where I just troubleshoot stuff. So F9, F5, F10. No, not click that. F10, F10. Yeah. So now it's gone to the right type. Yep. Destination index is that. Disp 50 is 255. Then F5. Okay. So now we're getting the next instruction, which should just be F10, F10, F10. Yep. Set to register. I've copied. Yep. Okay, F5. Then now we've got this instruction, which adds the two registers. Yeah, so it's running the right instructions now. So it adds the two registers. Um, adds a literal to the register. What's the lit 51? Lit 51 is 50. Yeah, so it's doing the right thing now. And then copy to memory. So, yep. And then memory.index F10. And then now that jumps to whole. Yep, yep. And then what should happen if I check memory 0xFF. If I go to memory, go to data, it should be memory data, should be memory dot data 0xFF 255. So why is it 255? What's that? Memory 100. Yeah, so no, so I think what's looking like the problem is that it's not. Why is it not adding the two value? It's not adding properly. That's why. I need to check the registers as well. Registers. Let me increase that. registers data registers dot data should be register 5. No, I didn't finish. Yeah, register 5 is not that. Register 6 is 0. Okay. So, um, hmm. We're actually gonna leave it like this for now because I cannot continue for much longer. But our program currently doesn't work correctly. However, the actual decoding is clearly performing the operations correctly, but there's something on the register side that's not right. But hopefully we'll fix that tomorrow. Get some more instructions done. I'll explain IO tomorrow, and hopefully, you know, we'll get more of this VM done, and then maybe we'll even touch on assemblers sometime soon, sometime later, right? This has been my first ever live stream. Actually, it was pretty fun. First one I'm actually gonna leave up anyway. 30. It's been about 4 hours ish, and all right. So I guess this is the end of the stream. Um, so in the stream we've made a pretty nice VM so far, I would say, and in next stream, which will happen tomorrow, we'll fix whatever's going wrong with this code. We'll implement some more instructions, and we'll have a look at how IO will be handled in the system, right? My name is Abdul Majid Raji. I own this channel, Min the Dimple. You can check out my blog, which is in my bio.